What happens when a star dies? Does it quietly fade into darkness or rip itself apart in a blast that can outshine an entire galaxy? Some stars end gently, others explode so violently that they scatter the very elements that make up planets. And you. In this video, we're climbing the collapse ladder of stellar death, from red giants and white dwarfs to supernovae, neutron stars, and the most extreme stripped core explosions in the universe. How far can a star fall? And why does its destruction make life possible? Let's find out. Level 0. Red Giant Star. Level 0 is surprisingly chill. The red giant. This is what happens when a star swells up and cools down so much that its color shifts toward the red. The cooling of an expanding star causes it to glow redder, which is exactly why we call it a red giant. In this phase, the star's size becomes enormous compared to its earlier life. Red giants can be between 20 and 100 times the size of the Sun, but that huge puffy appearance is deceptive. Red giants contain between 0.25 and 8 times the mass of the Sun, so they're big in volume, not in mass. On our collapse ladder, a red giant is a star that has clearly left its stable youth behind, but hasn't reached a violent end. It has expanded, cooled, and changed color, yet it still holds together. The collapse here is mostly internal, changes in the star's core and structure that lead to this swollen, cooler, redder state. Level 0 is the warning sign. The star is transforming, and what happens next depends heavily on how massive it is. Level 1. Red Supergiant Star. Level 1 turns that quiet warning into something more ominous. The red supergiant. All stars will expand, cool, and change color to become either a red giant or a red supergiant. The deciding factor is mass. Red supergiants are the expanded cooled phase of more massive stars. These very massive stars burn through their fuel in a hurry. They use up their fuel quickly and may only last a few 100,000 years. Their lives are intense and short, and their later evolution is crammed into a brief cosmic moment. Massive stars that become red supergiants experience a much more energetic and violent end than smaller stars. In single-star models, an O-type star can be heavily stripped during a red supergiant phase before becoming a Wolf-Rayet star. More generally, to reach the Wolf-Rayet phase, an O-star must have been heavily stripped during a luminous blue variable or red supergiant phase. In most cases, that means losing its hydrogen envelope. So level 1 isn't just bigger red giant, it's a fork in the road. Red supergiants are the launchpad for some of the most energetic endings in the universe, and can be the gateway to the Wolf-Rayet stage that lies higher up our collapse ladder. Level 2. Planetary Nebula phase. Level 2 belongs to the smaller and mid-range stars, stars like our Sun. After leaving the red giant stage, a smaller star like the Sun will go through a planetary nebula phase. This isn't a core collapse supernova, it's more like the star gently shrugging off its outer layers. Mid-range stars that reach the tip of the asymptotic giant branch produce a planetary nebula with an extremely hot central star. At this point, the star can no longer keep its previous shell burning going, so its outer material is expelled. The expelled gas from a planetary nebula is relatively rich in heavy elements created within the star. Depending on the type of star, that gas may be particularly oxygen or carbon enriched. This material doesn't just disappear. The gas builds up in an expanding shell called a circumstellar envelope. As this circumstellar envelope moves away from the star, it cools and allows dust particles and molecules to form. On our collapse ladder, the planetary nebula phase is a graceful kind of disassembly. The star isn't blown apart by a catastrophic blast. It peels away its outer layers into space, revealing a very hot exposed core. That core is already on its way to the next level. The White Dwarf. Level 3. White Dwarf Star. Level 3 takes us to what's left after that gentle shedding, the White Dwarf. For a smaller star like the Sun, the path runs from red giant to planetary nebula, and then into this compact remnant. A smaller star like the Sun will go through a white dwarf phase after the planetary nebula phase. White dwarfs are the remains of a star roughly the size of the Sun when it runs out of fuel. During the planetary nebula stage, the star has already thrown off its outer layers. The central star of a planetary nebula cools to become a white dwarf. What's left is a dense, compact object that no longer powers itself the way it did in its main sequence life. But even at this quieter level, things can still get violent under the right circumstances. In a binary system, a white dwarf can undergo a thermal runaway supernova if it absorbs enough matter from its companion star. A thermal runaway supernova can also occur if two stars in a binary system, where one or both are white dwarfs, collide. White dwarfs in binary systems are progenitors of one type of supernova described as thermal runaway supernovae. So level 3 is a kind of crossroads. Alone, a white dwarf is a stable remnant of a sun-like star. Paired closely with another star, it can be pushed into a runaway event that completely disrupts it. Level 4. Black dwarf star. Level 4 is the quietest ending on our list, the black dwarf. After many thousands of millions of years, a white dwarf will stop glowing and become a black dwarf. Over this immense time span, it gradually radiates away its leftover heat. Black dwarfs represent the final cooled state of low-mass stars like the Sun. For a smaller star like this, the full progression is Planetary Nebula, White Dwarf, and eventually Black Dwarf. A black dwarf is the stage reached after a white dwarf has cooled for many thousands of millions of years. By this point, the star no longer shines. Black dwarfs no longer glow because they have radiated away their residual heat. The path to a black dwarf depends on the star being of relatively low mass, like the Sun. On our collapse ladder, level 4 is the ultimate slow fade. No explosions, no dramatic last act. Just a long, steady cooling until the remnant is dark and inert. For low-mass stars, this is the end of the road, a cold relic marking the final step from active star to silent remnant. Level 5, core collapse supernova. At level 5, the tone changes completely. This is where stars die loud. Here we meet the core collapse supernova, the colossal explosion of a star. Core collapse supernovae occur in the last stage in the life of massive stars that are at least 8 times larger than the Sun. Throughout their lives, as these massive stars burn fuel in their cores, the heat they produce generates pressure that pushes outward against gravity. That outward pressure balances gravity's inward pull and keeps the star stable. When the star finally burns through its fuel and begins to cool, the outward pressure drops. With nothing left to counteract it, gravity suddenly takes over. Gravity causes the star to collapse in seconds. This collapse of a massive star produces the explosion known as a supernova. After a core collapse supernova, all that remains is a dense core and hot gas called a nebula. The nebula is the expanding cloud of material blasted outward, while the dense core is the compact remnant left behind. Level 5 is the dividing line between quiet endings and explosive finales. The core implodes, the outer layers are blown away, and the star's original structure is destroyed in a single colossal event. Level 6, Nucleosynthesis in Supernovae. Level 6 zooms in on what that explosion actually does to matter itself. As a massive star collapses in a core collapse supernova, it produces a shockwave that can induce fusion in the star's outer shell. This isn't just a blast wave tearing things apart, it's powerful enough to trigger new nuclear reactions in material that was previously more stable. Fusion reactions induced by the supernova shockwave create new atomic nuclei in a process called nucleosynthesis. This is where many of the universe's heavier elements are made. Supernovae are considered one of the original sources of the elements heavier than iron in the universe. The consequences reach all the way to you. Even the iron in human blood can be traced back to supernovae or similar cosmic explosions from before the Sun formed. Supernovae are essential to life because they create many of the elements needed for biology. And the story doesn't stop with the explosion. Material scattered by a supernova explosion can later be incorporated into nebulae that form new stars. So level 6 is about destruction that doubles as creation. One star's collapse and explosion helps seed the raw material for future stars, and for the chemistry that makes life possible. Level 7, Neutron Star remnant. Level 7 follows what happens to the core that survives that blast, the Neutron Star remnant. After a core collapse supernova, the remaining dense core can become an ultra-dense neutron star if the original star was not especially large. Massive stars that explode as supernovae can leave behind very dense neutron stars. In massive stars, the core eventually becomes massive enough that it cannot support itself by electron degeneracy and will collapse to produce a neutron star or black hole. Neutron stars are one possible final state of massive stars after core collapse. These remnants can behave in dramatic ways. Neutron stars left by supernovae can spin rapidly. Rapidly spinning neutron stars can give off streams of radiation known as pulsars. In those cases, the star's rotation and magnetic fields combine to send beams of radiation sweeping through space. On our collapse ladder, level 7 is compact but extreme. The outer layers have been blown off in the supernova, but the core survives in an ultra-dense form. Whether or not it shows up as a pulsar, the neutron star is the direct product of a core that could no longer support itself, and of the violent collapse that followed. Level 8. Wolf-Rayet Star, WR. Level 8 takes us to a special, highly evolved class of massive stars, Wolf-Rayet stars. These aren't final remnants, but they are advanced, heavily stripped stages in the lives of very massive stars. The evolution to the Wolf-Rayet phase can only be attained by the most massive stars with initial masses greater than 25 solar masses. To reach the Wolf-Rayet phase, an O-star must have been heavily stripped during a luminous blue variable or red supergiant phase, and in most cases have lost its hydrogen envelope. In single-star models, an O-star can be heavily stripped during a red supergiant phase before becoming a Wolf-Rayet star. Wolf-Rayet stars are known for their powerful outflows. Their winds are dense, with mass loss rates of about 10 to the power of -5 solar masses per year. These fast, dense winds help strip away the star's outer layers, exposing deeper regions. On our collapse scale, level 8 is a pre-supernova warning sign for the most massive stars. The star has already lost much of its outer hydrogen, and intense mass loss is reshaping it from the outside in. From here, different paths of stripping and core evolution lead to several types of core collapse supernovae, especially the stripped envelope kinds we're about to climb into. Level 9, Type 2, B core collapse supernova. Level 9 introduces one branch of those stripped envelope explosions, the Type 2 B core collapse supernova. These events are defined by how much hydrogen the progenitor star has left. Type 2b supernova progenitors have lost most of their hydrogen envelope. More precisely, they retain less than 0.5 solar masses of hydrogen. That partial loss is what sets them apart. The degree of hydrogen loss in the progenitor distinguishes Type 2b supernovae from other core collapse types. Type 2b supernovae are part of the stripped envelope core collapse supernovae group. Together, stripped envelope core collapse supernovae represent about 30% of core collapse supernovae. Within this group, nitrogen sequence Wolf-Rayet stars, which are hydrogen-poor but helium-rich, are anticipated to end their lives as Type Ib or potentially Type 2b supernovae. On our collapse ladder, level 9 is a star that's been heavily stripped but not completely. Enough hydrogen remains to affect the character of the explosion, but most of the envelope is gone. Its earlier life, through phases like red supergiant or Wolf-Rayet, has already peeled away much of its outer layers, setting it up for this particular kind of core collapse finale.